Okay, so we're going to start with an equilateral triangle and a point M on its plane. This dashed black circle represents the circumcircle of the equilateral. And I'm going to now draw 3 lines from M to each one of the vertices of this equilateral, like so. So I'm going to draw a line from M to this vertex, to this one, and to this one. And each one of these pairs of lines defines a subtriangle. So the first subtriangle is this one. It has, so imagine you have a side of the equilateral, and the 2 lines from M to this vertex and to that vertex, and then I have these other 2 subtriangles here, and I can compute the circumcenter, x3 of each one of those subtriangles, and I can connect them and define this, let's call this first generation green triangle. If I move M around, then the green triangle moves around because the 3 subtriangles change, right? So if I go to the interior of M, for example, and let's move M down here, I have these 3 subtriangles now, and I have the 3 circumcenters of each one of these subtriangles. Okay, now let's move M back to the outside, for example over here. Let's scale this down a bit. Maybe I'm going to move M down and then out a bit so that this triangle is more visible. So the first generation triangle is more visible. Let's now compute the second generation triangle. So I'm going to do the same construction, keeping M where it is. I'm going to draw 3 lines to the vertices of the green triangle. Okay, and those 3 lines are going to define 3 new triangles, subtriangles of the green triangle. And then I can compute their circumcenters, x3, 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 and define what I'm calling a second generation blue triangle. And then I can repeat this. Let's do the same thing and get a third generation. Now, the first thing you'll notice here when you get the third generation is that the third generation triangle is also an equilateral. And if you go to the fourth generation, you're going to notice that the fourth generation is similar to the second generation. Did I say this right? No, to the first generation. So the fourth generation is similar to the first generation. That's why they're color-coded both as green. And let's go now to the fifth generation, which is this blue one. Did I say this correctly? Yes. So this blue triangle here is similar to, so the fifth is similar to the second. Now what happens if I go to the sixth generation? I get a new equilateral. So what you start to see here, and this is true for any M, is that there will be only 3 distinct triangles, okay, in this iteration, in the successive sequence of iterations around these x3 based subtriangles. If you keep repeating this, you're going to get a sequence of triangles, and there's only, modulo rigid transformations and uniform scaling, there's only 3 distinct triangles in this iteration. So there's the original one, the equilateral. Then there's the first generation one. If we go back to the first generation, is this green one. Then there's going to be a third generation, and that's it. There's only these 3 triangles involved. And along the sequence, they're getting scaled down and rotated. Okay, we're going to develop these details more and more, but in this video I just want to show you guys properties of this recurrence or of this sequence of 3 distinct triangles. In fact, if you keep repeating this iteration, you're going to notice that the set of 3 triangles is slowly going to converge to M. So now I have 28 iterations. Let's go ahead and increase this to, say, 100 iterations. And I'm going to take out the construction lines. And you're going to get this sort of logarithmic spiral of triples of triangles that converges to M. Now, where does this converge and where does this not converge? Let's go ahead and draw this. It turns out the areas on the plane which are green, okay, the areas on the plane that are light green, this of course shoots off to infinity, they are areas where the series converges, the series of 3 triangles. So the series has a periodicity of 3 modulo homothecies, meaning there's only 3 distinct triangles, and they keep repeating themselves. And the triples, the consecutive triples, they're actually rotated and scaled with respect to point M, wherever you choose M to be. So let's look at M again. M is over here, right? So every new triple that comes out of this sequence is a repeated triple that is rotated and scaled with respect to M. And if the scaling, the consecutive scaling is less than 1, so if the rate of scaling is shrinking, okay, you're going to get something that converges at M. So what happens, for example, if I move M around? And I hope this thing doesn't freeze. I'm going to try to move M around in this region. Yes, I'm moving M around in the region. You can see here that as M moves, I keep getting this sort of sequence of, just for visualization purposes, focus on the sequence of quadrilaterals, or on the sequence of blue guys, or on the sequence of green guys, because they're repeating themselves and they're converging into M. Let's look at what's happening near Convergence Center. So I'm going to center the image on M, and I'm going to scale it up. So you can see here that you get a sort of tourbillon, right? You get this tornado. Let's increase the number of iterations around M, and it's a logarithmic spiral kind of tornado. So I have 90 iterations now. Let's scale this out again. Okay, and you can see where M lies on this region of convergence and divergence. So if M jumps over to the red region, this thing is suddenly going to start diverging. And let's look at what's happening here. I'm going to start sliding M slowly up. So I'm going to start sliding M slowly up. And perhaps I have to do this manually or using the cursor here, the slider. So M is now approaching that boundary of divergence. Now what's happening near the boundary of divergence, let's reduce the number of iterations, is that the rate at which these copies, these rotated copies of the equilateral. So it's a surprising thing, right, that we only have 3 distinct triangles over the series, regardless of where M is. And by the way, we could have started the series with any old scalene triangle. It doesn't have to be an equilateral. This would have introduced some distortions on these regions. They would not have this sort of threefold symmetry. But as M approaches the boundary here, the rate at which these triangles are getting scaled down is approaching 1. Okay, so where M is going to be right on the boundary, and let's keep moving M up here, where M is right at the boundary. I'm almost at the boundary here, right? Now my rate of scaling down is more gentle. Okay, so let's introduce more iterations here. And when M is exactly on the boundary, which I might be able to concoct slowly like that, you're going to get what we're calling a stable region. So there's going to be a circle in here beyond which the successive iterations cannot reach. So I'm going to go ahead and put on the screen here 200 iterations. And because M is right on the boundary, I no longer have a shrinkage phenomenon from generation to generation. All the 3 triangles, the distinct 3 triangles, have the exact same area. So all you're going to be doing is gyrating the set around M in such a way that you don't have convergence nor divergence. But when M penetrates that region, so now let's reduce the number of iterations here to say, I don't know, 62. And I'm going to penetrate this region by nudging M upward just a little bit. So I'm going to nudge M upward into the red region. And what you see here, if I scale this out, is that now, unlike in the previous cases, successive generations are amplifying the size of successive triples of triangles. So, their area is just slightly getting nudged up from successive generation to generation, such a way that if M lies in any one of these red regions, you're going to get this phenomenon where you get this progressive amplification. The further in M is into the region, let's move M even further up, you're going to see that from generation to generation in here, you're going to get further and further amplification, so that if M is in the interior of these regions here, for example over here, okay, and if I scale this up, now my factor of amplification is enormous, so this thing clearly diverges. And it's going to diverge all the way until M reaches the other, say, green area here. So let's keep nudging M to the left. I'm going to do it like that. So when M passes through the region here, as we did before, now we have a scaling factor of equals to 1. So if I increase the number of iterations, I'm going to be on that circle again. I'm not going to be moving inward anymore. Okay. Now, as M traverses into the green region by moving it further to the left, so now I'm going to get a tourbillon of sorts, a tornado of sorts. So let's scale this up. I'm going to center this on M. I'm going to scale this around M. You can see here that the generations starting from this guy here all the way to M are actually converging. So you have this sort of a chirality thing. If M is on one side of perhaps this altitude of the original triangle, so there's, if you can imagine here, an axis of symmetry for this green region here, which is shooting off from this vertex of the equilateral through its centroid and via an altitude, so there's an axis of symmetry here. So if M is on one side of the axis of symmetry in the green region, you twist to the left, and if it's on the other side by symmetry, you're going to see here that I'm going to twist to the right. Okay, now if I move M up a bit like that, so if I'm right on the axis of symmetry, for example, approximately here, I don't have any twisting, any chirality to this sequence. I just have a sequence that converges to M. Okay, now what happens if M is, so actually before we do this, let's go ahead and explore the geometry of this twisting a bit more, hoping that this guy is not going to freeze. You can see that all these guys within the green region are converging to M, and there's only 3 distinct triangles. Okay, let's go over to an area that is closer to the equilateral. So I'm going to lower M to be closer to the equilateral. Okay, and I actually want to be at a point at this black point here that I've marked here. In fact, you can see that these black points here, they are symmetric, right? They have this threefold symmetry, and these guys out here also have threefold symmetry, right? So let's recenter this guy. So I have these 6 points, these 6 black points here, that are, let's say, the closest points of each one of the green regions to the centroid of the equilateral. And something really magical happens if M is exactly on one of these points. So let's actually place M in this region here. Let's go ahead and they're symmetric, right? So let's go through the region of convergence, and I'm going to try to place M near that black dot over there. So I'm going to place M near the black dot. And you guys are going to see what happens when this happens. Okay, let's reduce the number of iterations. Now as M approaches that black dot, for example over here, now let's go ahead and do some iterations. Okay, the iterates, the triple iterates here, they become closer and closer to each other. Okay, now let's go ahead and make M, so the y coordinate of M be exactly 0, so that all my iterates they are all isosceles triangles. Okay, but when M actually reaches that critical point there, something magical happens. There it is. All my iterates are identical. So the triples are identical now. So I can iterate this 1,000,000 times, and I'm only going to have these 3 canonical triangles. Okay, so if we go back to basics, start with the red one. My M is right at that critical point. I'm going to do my first iteration here. I get this green triangle, this first generation canonical. Then if I go to the second generation, I get this second generation canonical. And now if I iterate with respect to this blue one, let's draw the construction. Okay, I think to see that I need to go third generation. Yes, so believe it or not, this blue triangle here through this x3 subtriangle iteration is going to send me back to the red triangle, and then the red triangle sends me back to the green and to the blue, and I never escape this period 3 iteration. Okay, and the same thing happens. So let's now try to carefully move this over to the other side, and I have to just hope that this thing is not going to freeze. So I'm just going to lift this a little bit. I'm going to put a bunch of generations here, and I'm going to move M slowly to the left. So I'm going to cross over. So let's start all the way on the right. I start on the right, then I'm going to start moving to the left. I'm going to cross over just a little bit above that critical point. Okay, then I get into this region of divergence. Then I get into the triangle. By the way, all points, you know, if you get rid of these iterations, you're going to notice that all points that are interior to my original triangle are unstable. They are diverging points. Okay, so if I start the iteration from M interior to the triangle, I'm going to diverge. Let's look at that divergence. Why? Because, and I didn't explain to you guys how I computed these regions, but the interior of the triangle is red, right? And there's an area here around the exterior of the triangle that is all red as well. So for you to actually escape divergence, you have to go over to the green side. Okay, so let's escape divergence. I'm diverging here. I'm going to continue to move M to the side, and then all of a sudden I'm converging. I'm converging over here, right? So I can move Y up and down. I'm converging. But what I want to show you guys is what happens when I'm at this other black point here, this one over here. So let's move M toward it. And I'm going to scale this up a bit so we can see it better. And I'm going to move M toward it. And let's go ahead and move M down a little bit. I'm over here, and I'm going to make my Y coordinate for M go back to being equal to 0. So you guys can see that this is always spawning off a sequence, converging in this case, and diverging if I'm on the other side of isosceles triangles. Okay? Now, what happens when M is exactly equal to this black dot? So let's keep approaching M to it. And you can see that my triangles are becoming closer and closer to each other. So when M is exactly equal to that point, and now they're actually converging, you're going to get a second canonical effect. You're going to get 3 canonical triangles, which are different from the 3 canonical triangles we obtained. So this is an infinite recurrence. Okay, so you only get these 3 if you iterate indefinitely. You're only going to get these 3 triangles here. Okay, if M is in this position here. And by the way, if M is on that position there, you're going to get the same figure, but rotated 2 pi over 3, 120 degrees, right? So these 3 canonical triangles are generated whenever M is in one of these 3 black dots. And let's go back to that position there. So these other 3 canonical triangles are generated when M is over here. Now, are these 3 canonical triangles? So by the way, if M is here, or at that knee point there, or at this knee point here, okay, if M is on either one of these 3 points here, you're going to get this canonical. Now, where is this M here? For the equilateral case, you just need to move from this vertex over here 1 side length to the right. So this distance here is equal to a side length. Okay, and this distance over here, from here to over here, is equal to a square root. It's 1 minus square root of 3. Okay, so if this point here is 0, 0, and this is 1, 0, this point here is 1 minus square root of 3, 0. Okay, so we have these 2 situations here with this infinite repetition. Let's move M over to this side again, to that spot again. You can see we have these 3 triangles here and these 3 triangles there. Now, I believe these 3 triangles, if you swap the green with the blue, they are similar. Okay, so you see that you have this elongated blue over here that is going to play the role of the elongated green there, and this sort of isosceles, less elongated blue guy plays the role of this green one here that is inverted. Okay, so they are really the same 3 triangles with 1 swap, but we'll get this nice phenomenon here that the series goes nowhere and it just repeats and repeats itself. Now, the third special case that we want to look at is when M approaches the center of this picture. So let's keep moving M to the right. And now you get this divergence series, except that you're going to get one special case. So am I still diverging here? I'm in the red zone, right? So let's increase the number of iterations. You can see that I'm still diverging. But let's move M closer to that red dot, which is the center of my original equilateral. So I'm going to keep moving M to the center. I'm still diverging. And then when M is exactly at the center, you get a 2 periodic, which looks like the Star of David. Okay, so when M is exactly at the center, center equals, oh, I believe I can do this, right? I'm just going to put this guy equal to 0 and hoping that this thing is not going to freeze. And now I just have my foot. Let's scale this up. So if M is at the center, my iteration produces a second green triangle, and the iteration of the second green triangle is going to produce the original triangle again, and this is going to repeat indefinitely. So this is a very degenerate special case where M is exactly the centroid of my equilateral. I just have a period of 2. Everywhere else I have a period of 3. And here I only stay within these 2 triangles. So here I stay with these 2 triangles. If I go to this point over here, I have an iteration, period 3, right? And then if I move over to the one on the left, on the right, if I move over to this guy over here, I get an iteration of period 3. Okay, so this is the result, guys. As M moves around and I iterate my triangles, for example, 40 iterations, okay, I have these zones of divergence and I have zones of convergence. Okay, and the periodicity is 3, and every application of 3 transformations sends the original set of 3 triangles to a new set of 3 triangles, which is a rigid, rotated, translated version of the original triple, and it's rotated with respect to M. It's always rotated with respect to M in such a way that if you apply this multiple times, you end up getting a tornado around M, and the vertices of successive similar polygons are going to lie on a logarithmic spiral. So now let's just show off a few more positions of M, and you get these stunning phenomena here of if we scale this up, right, logarithmic spiral type phenomena. And it seems like this is happening for any position in the green area. Oh, by the way, just as a final note, how did I compute these regions? Okay, these very interesting looking green and red regions. All you need to do is the following. You're basically looking at 3 applications of this transformation, and you're looking at the first copy, so to speak, of the equilateral. And all you need to know is you're going to mark green the areas of for which the first copy of the equilateral has a smaller area than the original one. So the green areas here are positions of M where this first equilateral's area is smaller than the original one. And the boundary itself is when the equilateral has an area that is equal to the original one. For example, right here, if I move M just a little bit to the left so that I get to that position, you're going to notice that if I take my iterations back down, the first iteration equilateral, this one here, has an area that is numerically identical to this one, in such a way that if you iterate the series, you're never going to be shrinking it down. These are simple rotations about M of the set, and they're not shrinking down. There's one more phenomenon that is a little unstable numerically, and I'm just going to finish the video with it. What happens if M lies on the circumcircle of the original triangle? So let's scale this up and let's investigate this. I'm going to nudge M, wherever M is, if I can see it. M is over there. Let's nudge M. I'm in the converging area here, in the green area. I want to nudge M so that it's closer to the circumcircle. Okay, so let's nudge M over there. And now let's look at what happens in that very first iterate. Okay, the very first iterate. So I'm going to go to construction, and this is usually when my simulation freezes. But let's try to look at this. So let's focus on the central area here. Okay, and I'm going to take off the boundary for now, and I'm just going to nudge M toward the circumcircle. And let's look at what happens to my first iterate. As I do that, the 3 subtriangles start becoming triply inscribed on the original circumcircle. So when M is exactly on the circumcircle, these 3 triangles are going to share their circumcircles with the original triangle. So in such a way that the 3 circumcenters are going to start collapsing to a point that coincides with the original centroid. So you can see that collapse going on. Now what's happening in terms of the second generation? Something very interesting happens. The second generation starts becoming a degenerate polygon. a line or a segment line polygon. So let's look at that. So you see, my second generation blue polygon is approaching a line. Of course, when M is exactly on the circumcircle, I cannot even compute the 3 circumcenters because this is going to become a point-like first generation triangle. So I can't compute the circumcenters of a point-like first generation triangle. Therefore, nothing here is defined. So in this discussion, we have to exclude points where M is exactly on the circumcircle, and furthermore, when M is exactly on the sides of the original triangle. Well, let's just look at this iteration just for fun. And I'm going to turn off my construction. I'm going to scale this out. And I'm just going to look at this iteration here. So as we know, we're always going to have, let's scale this up. And I'm going to move M a little bit away from the circumcircle. Okay, so we can see this a bit better. Let's scale this up. So I start with my red triangle. I have my first generation that wants to become point-like at this original centroid. Then I have my second generation. And you can notice here that M is a little bit away from the circumcircle. Let's make it go a little closer. Okay? So my first generation is a very small triangle. My second generation wants to become an infinite segment. My third generation is this copy of my first equilateral, third generation. And here's my fourth copy of that. When I say copy, scaled and rotated about M. Okay? And then so forth and so on. So you're going to get a sequence of line-like second generations. Okay? So when I say second, I mean the second, the fifth, the eighth, the 11th. Okay, so nth generation mod 3. Right? Now let's go ahead now and nudge M again closer to the circumcircle. I'm not quite yet on the circumcircle, but I'm pretty close to it. Actually, now I'm inside of the circumcircle, but now I'm pretty close to it. I add some noise here so that M cannot be exactly on the circumcircle. Now you can see here that all my first generation triangles are starting to collapse to these really tiny green dots here. Okay, so there's a green dot over here. There's the original one there, first generation. Here's the fourth generation. Here's the seventh generation, so forth and so on. And what I'm going to end up getting is a collection of equilaterals, dot-like second generations, and line-like third generations. But they still collapse. They still converge. Let's bring our boundary back in because I'm still in a green zone here. Oh, actually, I'm on a red zone. So, yeah, let's scale this up. So this is a diverging series. Let's now put M in an area where it's converging, but it's near the circumcircle. So I'm going to go back to my converging area here, and I'm going to move M down. Let's move M down. Let's take the iterations out. I'm going to move M down a bit. So for example, over here, and let's do 1 iteration, 2 iterations, 3 iterations. So now I have a converging series of equilateral followed by dot-like first generation, followed by line-like second generation, and so forth and so on. And they're all rotating nicely until they reach M, like so. Okay, so if I nudge M just a little tad, and M is over here, I'm going to nudge it just a little tad to the right. So now my line-like and my dot-like truly become dots. They're almost dots now, and I'm just getting a sequence of, you know, I'm an epsilon away from the circumcircle now. So I'm getting a sequence of equilaterals, followed by dot-like triangles, followed by line-like, segment-like second generation triangles. And that repeats until I converge. Let's look at what this convergence looks like as I scale up my simulation into M. And I'm getting the same pattern here. Let's increase the number of iterations. And you get the same pattern. So it's a pattern of equilaterals, dots, and segments. Okay, scaling this up. And of course, if I'm going to move, and I don't have a mechanism to do this here with the current simulation, but it would be nice for us to move along a circle that is just epsilon away from the circumcircle to see what happens to this pattern. Okay, but right now I haven't implemented this, and all I have right now, so if I move M away, safely away, I get this pattern. if I move M all the way up to that other zone up there, so let's just move M all the way to the left here, and just gonna move M up. I go through this divergence area and then back to my convergence area up there. I'm safe again. Okay guys, so I guess this is it. This has been a bit long-winded, but I wanted to show you guys a bunch of the phenomena that are taking place here with these iterates of X3 subtriangles, and how they can become stable or unstable, converging or diverging, depending on which region this M object here lies on, this point. Okay, so I hope you got a sense of what the phenomenon is. And of course, I could have started with a scalene triangle and would get the same 3 periodicity. Okay, so this is something we still don't understand. Why are we getting 3 periodicity for whichever starting triangle we get? Alright, see you on the next video. Thanks for your time.